Okay, I'm going to do something on radians now, which is more A-level and IBAC than anything else. So I'm going to start off by just doing a couple of things. So to go from degrees to radians, you basically times by pi over 180. That is because a whole circle in radians is 2 pi. So 360 degrees equals 2 pi. So if we were going to convert that, we'd go 360 times pi over 180 equals 360 over 180 pi, which equals 2 pi. Okay, and to sort of give you another example, 45 degrees would be pi over 180, which would be 45 over 180, which is 4, it goes in 4 times, so it's pi over 4. And the point is that 360 degrees is kind of an arbitrary thing that we've used for years, but radians make more sense in some ways because they're not quite so, what's the word? They're not quite so random. Now, what you can do if you want to go from radians to degrees is exactly the opposite. So from radians to degrees, we times by 180 over pi. So say we have, I don't know, let's go for something really obvious. So pi, you would times that by 180 over pi, and that gives us pi and pi cancel out, so we get 180 degrees. What about pi over 6? Well, that would be times 180 over pi. You get rid of both the pi's, and you get 180 over 6, and that is 30. So because you've grown up constantly thinking in degrees, because you can't help it, you see 90-degree angles everywhere, like in your room or around, it's sometimes easier just to carry on thinking in degrees and then just do this. So degrees to radians, we go pi over 180. Radians to degrees is 180 over pi. Just remember the pi goes on top for the one where you've actually got to do it. And in your calculator, you press shift and then menu setup. And then you can go into degrees that way. Right, I'm also going to do, we know trigonometry exact values. We've done that in another one of the videos. But you do also need to know the small angle approximations. So I'm not going to derive them. There are plenty of videos. ML Maths does them really well. So sine of pi equals pi. I'm so sorry, sine of theta equals theta. Tan of theta equals theta. And cos of theta equals 1 minus theta squared over 2. And then the last thing I was going to tell you is that if you want to find the area of a sector, now a sector is this sort of thing. So finding this bit. So if we were doing that in degrees, we do whatever this was. So that was, say that was 45, we do 45 over 360 times pi r squared. So basically we'd find the area of the circle and then find the fraction of it, and that would be 1 over 8 times whatever that was. But in this case we do area with radians equals half r squared theta. And then if you want to find, and this bit will require me to use another area, if you want to find, say, that bit there, the circumference bit of the sector, that one's really easy. So the sector not circumference, but the sector arc length, as it were, so this bit there, that actually literally equals whatever the r is times theta. So it's theta r. And you'll see how this works as we go through. Right. I'm not sure that's that interesting. So we'll start off with And I'm not going to do any of the things. So a sector of OPQ of a centre circle O has a radius of 4 and a central angle of pi over 4 radians. See, I still think of that as being 45 degrees, but anyway, and this is 4. So find the length of arc PQ. So we're actually just trying to find this. And the nice thing about this is that it is going to be, so PQ equals pi over 4 times 4, which equals pi, which is quite nice, isn't it? So finding the area of the sector would equal, now let's use the formula again, so it's half. It's a little bit like a triangle, but then again, if you look at a sector, it does look very much like a triangle, doesn't it? Times r squared times theta. So that equals half times 4 squared times pi over 4. So that equals 16 over 2 pi over 4, which equals 8 pi over 4, which equals 2 pi, which weirdly is 360. Okay, let's see if we can find a few more. I'm not going to fill in all that because, well, it's fairly obvious. Now, given that pi, or theta, excuse me, is smaller measured in radians, use the small angle approximations to find the approximate value. Two other things. One, you can't do this without using radians. And secondly, and this is very important, you can't differentiate or integrate if you're not using radians. So they are really important in that way. Anyway, so sine theta plus cos theta equals sine theta goes to, I'm just going to do that, theta, and cos theta of small little things equals 1 minus over 2. So if we add them together, we get theta plus 1 minus theta squared over 2, which equals, I'm not sure how useful this is. I suppose we could times that out. So we could do 2 theta plus 2 minus theta squared, and that I would naturally arrange that to theta squared plus 2 theta plus 2, or it could still be that. I don't like the way that's written. Right, or divide through by 2 and just make that what it was. And then 2 tan squared theta minus cos, so 2 tan squared theta. So if tan theta, basically we know that that's going to be, so tan theta equals theta, and we know cos theta equals 1 minus cos 1 minus theta squared over 2. So 2 tan squared theta equals 2 theta squared minus 1 minus theta squared over 2. And I'm going to do the thing which annoys me the least. So let's just do 4 theta squared minus 2 minus theta squared. Now, that's minus theta squared, so we're going to end up with 5 theta squared, and then that's actually minus 2. Or it could be 5 over 2 theta squared minus 1. I don't really care which one you want to do. I'm going to stop now because that's just a little introduction, and I'll do a bit more in a minute.